Welcome back to the second part of the videos on extended set difference. I wrote here the definition that I wrote in the previous video. And I want to talk a little bit about some properties of this difference, and then something about the uniqueness and so on. So first of all, let's see if that definition makes sense. So first property, let's look at some properties, and we list a few of them, but let's look at some examples. So first of all, what will be the extended difference between A and itself? And luckily, this is unique, and it's just a set. It includes the 0. So that's a good result. Another good result that we would like to have is that if we take A, Minkowski summation B, okay, a new set, and subtract from it B, we will get A. Okay, so that's again very nice, desirable result. Another result that we will have, that if we have a constant lambda bigger than 0, a real number, okay, then if we take lambda and multiply it by A minus extended difference B, it's equal to lambda A extended difference lambda B. Now here, that's a little bit of abuse of notation, because this is a collection of sets, and lambda times this collection of sets is we multiply every element of that collection by lambda. This is also a collection of sets here, okay, because there is no uniqueness, but it's the same collection. That's what this claim is saying. And there are more properties that you can look in the paper. Another thing is that if we look at the set of solutions, okay, the collection of solutions here to this argmin, then A minus extended minus B, okay, is a convex collection. Okay, so it means that if there are two elements inside this collection and you take a convex combination, that's also inside this collection. Okay, so those are very nice properties. Now, another thing that you would like to have is some convergence properties. So let's think about AN converging in the Hausdorff distance to a set A, and a sequence of sets Bn, again, convergence in the Hausdorff distance to a set B. Okay. And we look at the sequence of A minus An minus extended minus Bn. Okay. And we want to compare it, okay, or what happens as n goes to infinity, to A extended difference B. And again, here we have to be careful, because there are potentially several elements in this collection and potentially several elements in that collection. And so we need to be careful here. So what we say is that exists a sequence of set X that you can find, called Xn. And each time, for each n, Xn is one of the elements in this collection. It will have a convergence subset. Xn will converge to some X star, such that X star is in this collection. Okay, so in that sense, we have this property of convergence. Okay, another important observation is to try, okay, the scope of the solution. So how many solutions are there, and how different are they from each other? Okay, so here we say the following. Suppose, okay, x1 and x2 are in this set of A minus B. Okay, it's a collection, so I'm not writing here element of. Okay, so this convex associated also convex combination of x1 and xb is also there. But let's say that delta will be, it's actually, I want it to be delta, okay, the Greek. It's going to be the Hausdorff distance between A and B plus x1, which is the same as the distance between A and B plus x2, because they are both solutions. They achieve the same minimum or infimum, okay? Then what is the difference between, what's the biggest difference that you can have between two solutions? So the result that we show is that the Hausdorff distance between x1 and x2, any two solutions, cannot be more than 2 times delta, this delta. Okay, so that's the scope. And if you want to see an example in which you can actually achieve the 2 times delta, again, that will be this example with A and B being the 2 segments perpendicular to each other of length 2 and so on, and delta is equal to 1, and you can find x1 and x2 that the distance, two solutions that the distance is exactly equal to 2 times 1. Okay, so that's the scope of the solutions. We also provide some results related to symmetry. Okay, so if the sets are symmetric around a certain point, and it implies something about the solution. And again, I send you to the paper to look at these results. Okay, so everything here is under the knowledge that the solution is not necessarily unique. So how can one achieve uniqueness or some kind of uniqueness? Okay, uniqueness. The problem with this criteria function is that it's not strictly convex. Okay, so there is no uniqueness. So here is what we will modify this. We will say that A extended difference B, and we are going to use a penalization for the x, will be now defined as the arg inf, again over all the x in kc, that will minimize the Hausdorff distance between A and B plus x as before. But we also add some penalty, gamma, time r of x, where r is a function from this k, kc to the real line, okay, strictly convex. And of course, since this is convex, plus a strictly convex set, then the whole operation here now is strictly convex, and the solution is unique. Okay, so we will call for a given r, again, we need to find a gamma which is positive. Okay, so that's important to say here. Okay, and then we can call x star, gamma, which is in this modified extended difference. Okay, probably it's good to have another notation here that with the r maybe here and a gamma, and you can make the notation more and more complicated. But suppose it is in this a minus extended minus where we take gamma and r b. Okay, and we take now gamma to be not a constant but something that goes to 0. Okay, so it will be gamma n. Okay, so we show that if gamma n goes to 0, okay, we put a lower and lower weight on the penalty. Okay, r is fixed. Then you will eventually converge. Okay, the x star gamma n, as n goes to infinity, will converge to some x star, okay, which is in the regular A extended B. Okay, so we really just pick out one of the possible solutions in A minus B, and which one is it? It depends on the penalty that we add here to this infimum. So again, in the paper, I send you to the paper, you can see some examples and some natural examples there, and what kind of R can be thought here that will be strictly convex, and so on. Okay, so that's of course a user. So as you change R, you will eventually converge to another solution in the set, and we give some examples there. So that's about properties, uniqueness, and so on. Apart from additional examples and pictures and how to think about this difference, we, for example, show that you can subtract from a pentagon minus a square and what happens there and so on. So all sorts of different shapes and sizes such that this concept exists. Okay. What we also provide in the paper is a computational method, an algorithm to compute a solution from the extended difference set of solutions or collection of solutions. And we have there the algorithm and the examples, the pictures in the paper were produced with this algorithm. And if you write us, we can send you a Python code that implements the algorithm that we outline in the paper. Okay. So again, I will put a link for the paper, but to summarize, this is a new difference concept. There are other that I didn't review that also don't necessarily exist always and so on, but this one always exists, and it has some reasonable properties here. We have more in the paper: convergence, the scope is reviewed, there are some results about symmetry, there are results about rotations and things like that, transformations and so on. We address the uniqueness, we give some examples, practical examples, and an algorithm in the paper. Again, thank you for watching, and this is it about the extended set difference. Thank you.